Well, today we're gonna enter the last section of chapter 7, but it's also kind of a long one, so we're gonna take the whole week to do it. And then be aware, a week from Thursday, there's gonna be our next exam. We'll go through chapter 7. And I think it's one of the harder exams of the semester. After that, the material gets a little easier, not easy, but easier. So we'll finish chapter 7 this week. We'll spend this whole week on the one section, and then next week we'll have a test on it on Thursday. So this last section is on solving trigonometric equations. We've already done a little bit of that in simple cases. We're going to expand on that greatly. These come up in the sciences quite a lot, these trig equations. And what we're going to do is we're going to put together the house that Jack built here. We're going to start with a little bit, and then we're going to do a little bit more, a little bit more. Each method is going to build on the last one until we can do more and more equations. So the first method is motivated by what we've already done. We recall that we could solve for an angle in a right triangle by simply taking an inverse trig function. That was all there was to it. That's the simplest case of solving a trig equation. For instance, if I have this triangle here, 5 and 7 and theta, I could say find theta. It's easy, right? You simply say the relation between the angle and the two sides is tangent is equal to opposite over adjacent. So tangent theta equals 5 sevenths. And now immediately in a right triangle, just write theta is the inverse tangent of 5 sevenths, and you're done. This works in any right triangle. Why? Because in a right triangle, the two unknown angles are both acute. They're both between 0 and 90. That puts them in the first quadrant. In the first quadrant, the inverse trig function always gives you the angle. So this we could immediately write inverse trig function only because we knew the answer was in the first quadrant. Now what we're about today is suppose we have a trig equation where we don't know the angles in the first quadrant. It gets a little more complicated. So I think that's enough. However, if we don't know that theta is between 0 and 90 degrees, like we do in a triangle, we'll call it 0 pi or 2 radians. Almost all of these we're going to solve in radians because that's what's mathematically useful more often. Even though in a lot of professions, maybe degrees are more important. You can always, we'll do some of the others, but we'll do most of these in radians with the idea you're going to be getting those in your classes here. So if we don't know that theta is between 0 and 90 degrees, I mean, I have quite enough room here. Let's just do that. What do? We have the following strategy that's going to build in stages here. Stage 1 is if the equation is such as that trig function equals a number, I'm going to abbreviate trig function here. It's not so easy in the right triangle. You can't say that for a trig function of theta, I guess I should say, equals a number. You don't just say theta equals that number. There's actually more than one solution. If we want to solve this for all angles theta, we solve it by the unit circle. Because there's actually an infinite number of answers in general, or sometimes no answer. And I want to just do this by example rather than writing out the strategy. The example shows it. Suppose I want to solve sine theta equals square root 3/2 for all possible theta, not just in a right triangle. All right. This will be our first kind of trig problem. Trig function equals a number. This is what we'll do. We'll put a unit circle down. And then we'll say, we've done a little bit of this before. Sine theta is the y coordinate on the unit circle, right? So that means, well, square root 3/2 is about 0.8 something, so it's way up here. Y equals square root 3/2. And now, since square root 3/2 is less than 1, it cuts the unit circle. A line that cuts the circle cuts it at exactly 2 points. That means there's exactly 2 terminal rays that go through those points, right? Which means there's more than one solution to sine theta equals square root 3/2. There's at least 2 terminal rays for starters. What are the angles of those terminal rays? So you drop the perpendiculars and make your reference triangles here, right? And you say, I know a side of that, right? This goes from 0 to square root 3/2, so this side length must be square root 3/2. And correspondingly, this one too. What you're going to find when you get these multiple triangles in the unit circle during this section, they're always going to be congruent triangles. That means all angles and sides are equal, are correspondingly equal. So this triangle, you could flip it over and land right on this one. If I draw it right. Now, this is a unit circle, so this side is 1. If this is 1 and this is square root 3/2 on a right triangle, there's only one choice for the last side. It has to be 1/2. The Pythagorean theorem would show you that. And this is a 30, 60, 90 triangle. In other words, pi/6, pi/3, pi/2 in terms of radians. So these angles are both pi/3. There we go. Now I see what my solutions are, right? My solutions, if I can move this over, are this angle, theta equals pi/3, or theta could be pi, straight angle, back up pi/3. Two different terminal rays. These both go to those terminal rays. I want to point out something that's a mistake on the test almost every time I get to the next test. Somebody will write this. What's wrong with this answer? Theta equals pi/3 and theta equals pi minus pi/3. It's a mathematical faux pas. Everybody knows you mean these are both solutions. This is a solution and this is a solution. But mathematically, if you say theta equals this and theta equals this, it means theta has to satisfy both equations, but it can't. These are different numbers, right? So it's a faux pas, even though everybody knows what you mean. It's improper language. What you should write is or. So on your test, I'd like you to put or. If you put and, I know what you mean, but it's technically wrong, right? So theta equals pi/3 or pi minus pi/3, which is 2 pi/3, right? This is 1 minus a third. 1 pi minus a third pi is 2/3 pi. So there's 2 solutions here. But wait a minute, I said all possible theta. What I've shown is there's only 2 terminal rays, and I've got an angle to each. What are all possible angles? There are any angles that go to these terminal rays, right? Well, any angle of these terminal rays is the ones we picked, plus any multiple of 2 pi, any whole rotations, right? All coterminal angles are just differ by a whole rotation, multiple of a whole rotation. So these go to the 2 terminal rays. So what are all the angles? Theta equals pi/3 plus k times 2 pi. This represents k rotations. or k could be any integer. It could be 0, 1, -1, 2, -2, 3, -3. Any number with nothing after the decimal point. So it's a whole number of rotations, plus or minus, right? These are all the coterminal angles that go to the first one. Then this one, 2 pi over 3 plus 2k pi, k times 2 pi, are all the angles that go to the second terminal ray. All right, now this is true, and I don't have any problem with it really if you're writing your exam, but I'll probably correct it for you even if I don't take off any points. Convention says that you're supposed to write the 2 first. You know, it's just like you don't put A3 usually, you put 3A, right? When you write you don't put X3, you put 3X when you write something down. Same thing here. This is written usually pi over 3 plus 2k pi, like that, right? And you can write the word or you can just put a comma and make a list. Both of those work, comma or. These are all the solutions. All right, these are all the angles to the first terminal ray. These are all the angles to the second terminal. That's what you do if I give you a question. Trig function of theta equals a number and say find all solutions. You write the unit circle, find all possible terminal rays, and then find all coterminal angles to those terminal rays. Any questions on that? Does it make sense? This is exceedingly important because every other method comes back to this one. I told you it's the house of Jago. We're going to do the next method that comes back to this method and uses this at the end. And then the third method will go back sometimes to the second method and then to this method. All the other methods boil down to rewriting a trig equation as trig function equals a number and solving it this way. So this is the most important part because you use it in about every problem. All right, so there's the first problem with sine. Now it can get a little bit trickier.
Do we take the first two as well and put them in the answer?
These two? These are the same. All I did was rewrite them. I put the k between the 2 and pi. So yeah, this is, oh, I see. So yeah, this is a good answer too. I'll accept this, but I might down below write this notation as preferred. I don't think I'll take off any points for that now. Okay, and then I should put on here, since we're just starting this, k is equal to 0, 1, -1, 2, -2. This is the list of integers, we call them. So k is any integer, people say. And this is convention. If somebody writes the number x, that's supposed to be any real number, any decimal number. But if I write, so x and y and z, everybody assumes those can be any decimal number. But if you write j, k, m, n, those things, people, and usually I, unless it's square root of -1, those things are assumed to be integers. So when I write one of these letters from here out, assume it's an integer, and if I write one of these, assume it could be a decimal number. What we'll do. Now, next example is a little harder. We're going to move these up a little bit. Suppose I do the same thing, but with the tangent. Suppose I want to solve tangent of theta equals minus the square root of 3. How about that? What's harder about this one? In some sense, it's not all that much harder. I can solve it for all possible theta. Since it's not a right triangle, I can't just say that theta is the arctangent of minus square root of 3. That is one solution, right? When you have tangent equals a number, the arctangent is always one solution. But like this case, there's going to be an infinite number of solutions. So let's see if we can find them now. There's 2 additional tricks when you're doing tangent or cotangent. Those are the hard cases. When I have that, I rewrite this as a quotient, minus square root 3 over 1. And having written it as a quotient, I now take the root sum square of those numbers. Square root of minus square root of 3 squared plus 1 squared is square root of 4 is 2. And I divide the top and bottom by that root sum square to write it as minus square root of 3 over 2 and plus 1/2. Why would I do that? Well, this is where I get the 2 from, is from root sum squaring these two The reason is that once I do that, this squared plus this squared will be equal to 1. And so this will be a point on the unit circle, right? The equation of the unit circle is x squared plus y squared equals 1. So by dividing by this, I'll make this squared plus this squared equals 1. This will be a point on the unit circle. And indeed, you can see it, right? Because square root 3 over 2 and 1/2 is the plus or minus on each, is a triangle that fits right into the unit circle. And so this will work for any quotient here. You don't, not just this special case, you just divide by the root sum square, this always becomes a point on the unit circle. So this must be y, and this must be x, a point on the unit circle, but there's one more. Can you guess what the other point on the unit circle is you can get? With the same ratio. Just take minus this over minus this, right? I can take plus square root 3 over 2 over minus 1/2. So there's actually two solutions. I'll put or in here. I hope you can read that. That could be y and that could be x. Those are the only two ratios of points on the unit circle that are equal to this number. So now it's the same strategy. When you have trig points equals a number, you draw the unit circle. But tangent is harder to find the point on the unit circle. There's 2 points, just like there wasn't with the sign there, but these are opposite side always on the tangent, cotangent. In this case, minus square root 3 over 2 for x is almost minus 1. So here it's out here somewhere. That. And then 1/2 for x is halfway up to, for y. No, I'm sorry, I put this backwards, didn't I? Sorry. This is y on top, minus square root 3 over 2, sorry. And x is a halfway out to 1 here. So here's the point on the unit circle I found, minus square root 3 over 2 for y and 1/2 for x. That's a terminal ray. When you're doing tangent or cotangent, the other one is always directly opposite because it's always minus this number over minus this number to get the same quotient. So this one will go through minus 1/2 plus square root 3 over 2. Just minus these two numbers. So directly opposite. And now we can do the same thing as we did last time. We can drop the perpendiculars and figure out what the angles are. This time I've got two sides. 1/2, since this goes out to minus 1/2, this side length is 1/2. Since this goes up to square root 3 over 2, this side is square root 3 over 2. This side is 1 because it's unit circle. Again, it's a 30, 60, 90. This must be a 60-degree angle, also known as pi over 3, right? Similarly, this one is also pi over 3. So I have two different angles. I can do the same thing as before. Find a good eraser here. All right. From that diagram, I now say two solutions, one for each of the terminal rays. Are evidently in the picture. I went pi over 3 like this, clockwise, so it's minus pi over 3. The other one was pi over 3, and maybe I should draw it over here since online you can't see it. We have this. This was pi over 3. There's a square root 3 over 2, 1/2 here. And this was pi over 3 on the other board. This is square root 3 over 2, and this is 1/2 here. And so the angles are minus pi over 3 since I went clockwise, and then pi back up pi over 3. Are minus pi over 3 and 2 pi over 3. So there's two solutions, but that's not all of them, right? What are all solutions? All solutions are all coterminal angles, all other angles that have the same terminal rates. Which means we can again add 2k pi to each of those, which is k whole rotations plus or minus. Theta equals minus pi over 3 plus 2k pi, or theta equals 2 pi over 3 plus 2k pi. This is a good answer. I don't think I'll mark you off on the test, but I will mark this surely because I'd rather you would write something a little easier. What could be easier than writing this down? Even though those are the right angles, what's a shorter way to write that down? See it? When these angles are directly opposite, what you can do this is just take either one of them, like this one, 2 pi over 3, plus pi, plus pi, plus pi, plus pi. It also gives all the angles. Instead of adding 2k pi to each, take one of them and just add pi over and over. So easier, you can write this succinctly as theta equals either angle, it doesn't matter which one, 2 pi over 3, let's say, plus k pi, k half rotations. Here's the best way to write it, where once again, you don't have to write this down, but we're tacitly assuming, because everybody knows that's what you do by convention, that k is an integer, 0, 1, minus 1, 2, minus 2, etc. on forever. So there's all solutions to tangent theta equals minus square root 3. Well, what's another one we can do? How about secant or cosecant? If you have secant or cosecant equal a number, say secant theta equals minus square root 2. How about that? Solve that one for all angles theta. What can I do? Well, now secant isn't either the x or y coordinate, it's 1 over the x coordinate. What's easier to do if you have secant or cosecant is to immediately write the reciprocal. Instead of secant equals this, take the reciprocal of this equals the reciprocal of this, and you have cosine theta equals minus 1 over square root 2. So secant or cosecant, immediately rewrite it. Now you do it in the unit circle. But see, that's the trick. We have trig function equals a number, you go to the unit circle, but it's a little different for sine and cosine than it is for tangent and cotangent than it is for secant and cosecant. For secant, cosecant, just rewrite it as sine or cosine. Now, so cosine is the x coordinate, so I'll mark the x coordinate minus 1 over square root 2, which is about minus 0.7. And now x equals a fixed number. All those points are a vertical line, right? This is the line x equals minus 1 over square root 2. A vertical line at this coordinate, minus 1 over square root 2. If those are all the points in the plane that have that x coordinate, that shows, since it cuts the circle before minus 1 here, that there's exactly 2 points in the unit circle that have x coordinate minus 1 over square root 2. Therefore, exactly 2 terminal rays. And we can figure the angles. If this is that x equals minus 1 over square root 2, then the side length must be 1 over plus 1 over square root 2, right? The hypotenuse is 1. I know what right triangle that is. In fact, if I rewrite 1 over square root 2 by multiplying by square root 2 over 2, I find out that square root 2 over 2, oh, this is the square root 2 over 2, 1, square root 2 over 2 triangle. Pythagorean theorem will force this third side given these two. And I get a 45, 45, 90 triangle at pi over 4, pi over 4, pi over 2. Radians, those angles are both pi over 4. That being figured, we can now figure all angles, right? Those are all terminal rays of those two that I drew. So an angle to each is, well, pi back up pi over 4. 4 pi move forward pi over 4. All right, this is one pi minus a fourth pi is 3/4 pi. this is 1 pi plus a 4th pi is 5/4 pi, right? 1/4 is 5/4, all times pi. So those are two different angles, one to each terminal, right? Which means all coterminal angles, all angles to those terminal rays. Are these plus is removable 2 pi. K equals 3 pi over 4 plus 2k pi, k notations. Or 5 pi over 4 plus 2k pi. And these you can't combine. Why not? Because they're not equally spaced around the circle. Right, it's not plus pi, plus pi, plus pi. It's just when they're equally spaced around the circle, you do that trick of combining them. All right, so that's the first and most important trick there. Leave some of that off, I'm sorry if I did. Now, step 2, right? You're gonna build and build and build here. You'll be glad you came to this lecture because next time everything will seem just like a lot of Greek letters otherwise. The next step then is to solve Trig function equals a number. Just like we did. But for theta between 0 and 2 pi, that is within one rotation. Right? There are other ways to do this. Yeah.
Can you move the camera a little bit, please?
Yeah, the last word was off in that now.
Thank you.
So if I want to solve trig function equals a number, the same equation, but for theta restricted between 0 and 2 pi, and I want to introduce this notation here. When I write this notation, 0, 2 pi, that means this, right? Interval here means that x is between 0 and, or theta in this case, is between 0 and 2 pi. The square bracket means include equals. The round bracket means don't include equals. So this is just another notation for this. Right? You'll see that in the homework. Have to know both. This is common notation. But one way to solve this, and there are other ways, but I'll introduce this way because it plays with the next method better. You simply, by method 1, first find all angles and then throw the ones you don't want out. That seems pretty easy. It's not too hard. Let's try one of those. Again, let's try cotangent of theta equals -1. How would I solve that one? Restricted to theta between 0 and 2 pi. Again, we use the unit circle. And since it's tangent or cotangent, I'll rewrite this as a ratio. And then divide by the root sum square. So the root sum square of those two numbers are -1 squared plus 1 squared square root is square root of 2. So I'll write this as -1 over square root 2 over +1 over square root 2. And I'll say this could be the y coordinate and this could be the x. I'm sorry, cotangent is x over y. This could be the x coordinate and this could be the y coordinate. Or I can take minus this over minus this, and it's the same ratio. I could have 1 over square root 2 for x and -1 over square root 2 for y. And these points will be directly opposite each other on the circle. So I'll sketch it here. I can go out with x equal -1 over square root 2, about -0.7, something like that. And y plus 1 over square root 2. I've got this point here, and there's that terminal, right? Or X can be positive and Y can be negative, right? 1 over square root 2 minus 1 over square root 2. Then I go directly opposite to this point. Plot the perpendicular. Notice that since it goes out to minus 1 over square root 2, this side length has to be plus 1 over square root 2. The hypotenuse is 1. That forces the last side, if you remember your triangles. 1 over square root 2, if you rationalize, is equal to square root 2 over 2, right? These are equal numbers written differently. Oh, I know what that is. Square root 2 over 2, 1. This side must be square root 2 over 2 also. It's a 45, 45, 90 triangle. This is a 45-degree angle, pi over 4. And similarly, this one. Maybe I should draw it this way. Minus pi over 4. And now maybe I'll just move this back a little bit to the left so I don't have to rewrite this on the next board. What I now have is angles to the terminal rays. Well, I can go this way, pi over 4, that's an angle minus pi over 4. Since this is pi over 4 here, the angle to this, in standard positions, pi back up pi over 4, is 3 pi over 4. There's an angle to each terminal ray. So all possible theta to satisfy the Trig equation are these plus 2k pi, right? Minus pi over 4 plus 2k pi and 3 pi over 4, 2k pi. Method 1, right? But now we have to restrict this to angles that are between 0 and 2 pi. Those in the interval 0 to 2 pi as requested are what? You just try different values of k near 0. I'll try k equals 0 in this one. K equals 0 doesn't work because that makes this 0 and I get a negative angle, right? I need an angle between 0 and 2 pi. So, and if I make k negative, it's even a smaller negative angle. So k equals 0 or negative doesn't work. But I try k equals 1 minus pi over 4 plus 2 times 1 pi is 2 pi. That one is actually going to be, let's see, 8 pi over 4 minus pi over 4 is 7 pi over 4. That one works. Okay, so that's one angle. That's with k equals 1 in the first equation, first part. Now in this part, if I put k equals 0, this falls out. I get 3 pi over 4. That's between 0 and 2 pi, right? 3/4 is between 0 and 2. 3/4 pi is between 0 and 2 pi. Right? So I put k equals 0 on the second one, I get 3 pi over 4. Putting k equals 0 on the second. And these are the only two solutions. Because if I put k equals 1 here, I've got 2 pi plus something that's bigger than 2 pi. If I put k equals minus 1, then I've got 2 pi minus 3/4 pi, that's still negative. Negative doesn't work, it's not in here. So only k equals 0 gives you an angle between 0 and 2 pi. The second equation, only k equals 1 gives you an angle between 0 and 2 pi. That's what you do. You try little numbers near 0 and start to get negative. You say, oh, I went too far to the left. And start to get bigger than 2 pi. You say, oh, I went too far to the right. And it puts you in this interval here eventually. So there's solving a trig equation for angles between 0 and 2 pi. And if you're clever on this one, maybe I shouldn't move it over quite so far. I just point out first. If you're clever, you could just look at the picture and say, well, wait a minute. I can rotate around to here, and that looks like pi back up pi over 4 is 3/4 pi. And just keep rotating, and this is 2 pi back up pi over 4. That's 7/4 pi, and I could write down immediately, and you're welcome to do that on your test. I often do that. So you don't have to do this method of finding all the angles and then throwing them out. You could just start here and rotate around to the first one, Start here and rotate around to the second one and get those two angles that way by just going counterclockwise till you finish one rotation. Then you're done, right? That's a good way to do it too. The reason I did it this way is it plays into the next method nicely, right? So do it either way. Throw out some of them afterwards, or just make sure you rotate only counterclockwise. Method 3, right? We're starting to build. These are going to get more complicated. To solve a different equation, Trig function, I'm going to start abbreviating here, of not theta, but of a multiple of theta, like 2 theta or 3 theta, equals a number. So instead of trig function of theta equals a number, now trig function of a multiple of theta equals a number. How do I solve that? Let's say k theta. Not where k is an integer. To solve that, simply put, as substitute. That's a better word. Your favorite letter, let's say phi equals k theta. Finish trig function of phi equals the number, solve it by your previous method. Now, if you're restricted to 0 to 2 pi, throw out angles not in 0 to 2 pi. Now you're going to see that finding all of them, throwing out the extras is kind of nice. Because this one is harder to visualize when you have a multiple of theta. This again, I think. For example, suppose I had this one. Solve for all angles within rotation. In one rotation, 0 to 2 pi. Sine 2 pi, 2k, 2 theta equals minus square root 3 over 2. Now I have trig function equal to a number. It's trig function of a multiple of theta instead of trig function of theta, right? So instead of going to method 1, what I do is I first substitute phi equals 2 theta, and then I go to method 1, right? So substitute phi equals 2 theta to get the kind of problem we've just been doing. Sine of phi equals minus square root 3 over 2, which we can solve on the unit circle. By method 1, we then say on the unit circle, sine is the y coordinate, so I draw the horizontal line, y equals minus square root 3 over 2. I notice that there's 2 places where it intersects, and minus square root 3 over 2 is above -1. That means there have been 2 terminal rays, this one. I can drop a perpendicular on each. I'll get 2 congruent triangles, reference triangles. Since I went down to minus square root 3 over 2, it follows that this side length is square root 3 over 2, as is this one. Since it's a unit circle with 1, that leaves this side to be a half, Pythagorean theorem. And it means that this angle here must be minus pi over 3, right? Minus 60 degrees. This angle here must be plus 60 degrees. And I can figure, once again, I'm using method 1. I can find an angle to each terminal ray and then add 2k pi to each. Let's see, for this one, all you do is you first substitute phi equal to theta, solve it as usual, right? So now, an angle to each terminal ray is, well, evidently minus pi over 3 in this one. And let's see, we could say it's minus 2 pi over 3, or we could say it's pi plus pi over 3, 4 pi over 3, let's say, go that way. There's an angle to each terminal ray. All angles are all angles satisfying sine 2 theta, sine phi equals minus square root 3 over 2, is our phi equals these plus 2k pi. So there's all angles phi. Oops, I should have left a little more room here. That gives those terminal rays. And now, wait a minute, we're not done. We wanted theta. Phi is equal to 2 theta, so we just write 2 theta equals this. Now, if 2 theta, if this is all angles theta, I just divide this by 2. Then I get theta on the left equals this divided by 2, or multiplied by a half, let's say, on the right. So I multiply the whole thing by a half on each side. And I get theta could be a half of minus pi over 3 plus 2k pi, or it could be a half of 4 pi over 3 plus 2k pi. And now you have to distribute the half, right? Half to half. All right. This one times this one, plus this one times this one, right? What's a half times minus pi over 3? All right, you take top times top, and you get minus pi over bottom times bottom is 6. So you got minus pi over 6, multiplying a half times this, and then a half times this, the 2's cancel, and you get k pi. Or on this one, a half times 4 pi over 3. The 4 and the 2 part, they cancel, and you get 2 pi over 3. And then a half of 2k pi is k pi. 1/2 of the 2 cancel. There are all the angles theta that you can get. Oh, wait a minute. One more step. We want a theta between 0 and 2 pi. So solutions theta between 0 and 2 pi are gotten by choosing all k values that make it work. And it's in the last one. I try k equals 0 in this one, and I get minus pi over 6. Wait a minute, that's negative. K equals 0 doesn't work. I get a negative angle. If I choose k equals minus 1, it's even more negative. That won't work. I have to start going positive. So I try k equals 1. Minus pi over 6 plus 1 pi. What's that? Well, minus the 6 pi plus 1 pi is 5 6 pi, right? Because minus the 6 plus 1 is 5 6 all times pi. So I get 5 pi over 6 from that one when I put k equals 1. First equation. Now I try putting k equals 2. If I put k equals 2, I get 2 pi is 12 pi over 6. Plus minus pi over 6 is 11 pi over 6. That's what k equals 2 in this equation. That's between 0 and 2 pi. 2 pi would be 12 pi over 6. This is less than 2 pi, right? It's positive and it's less than 2 pi. So that's a good angle. Now I can try k equals 3. Well, k equals 3 is too big. I get 3 pi is 18 pi over 6, minus this one is 17 pi over 6. That's bigger than 2 pi over 6, right? 2 pi. So these are all the solutions from the first equation. When k equals 1, you get an answer between 0 and 2 pi. When k equals 2, you get an answer between 2. Now we go into the second one and say, well, if k equals 0 here, I just get 2 pi over 3 plus 0 is 2 pi over 3. That's between 0 and 2 pi. So this one I get by putting k equals 0 in the second equation here, second set of solutions. Then I'll try k equals minus 1. 2 pi over 3 minus pi, oh, that's negative, because that's 2/3 minus 1 pi. That's right, minus a third pi, that's negative. So I can't go negative. I won't get any answer between 0 and 2 pi. I tried k equals 1, or k equals 0, let's try k equals 1. 2 pi over 3 plus 1 pi. Let's say 2/3 pi and 1 pi. 2/3 and 1 is 5/3, all times pi. So when I put k equals 1, I get 5/3 pi in the second list of solutions here. Now, if I put k equals 2, I'm out, right? Because when I put k equals 2, I've got 2 pi plus a positive angle. That's bigger than 2 pi. That's too big. So what I'm going to get when I put phi equal 2 theta is actually 2 solutions from each part. And here they are. I've actually got 4 solutions to this equation. This one came from k equals 1 in the first equation. This one came from k equals 2 in the first equation. This one came from k equals 0 in the second equation. This one k equals 1 in the second equation. 4 different answers between 0 and 2 pi. And now you see why I'm doing this strategy of finding all angles and then throwing some of them out. You don't have to do it this way, but think about what the alternative is if you want to do it the other way. The alternative, if I would have stopped right here and said phi has to be between 0 and 2 pi, I would have only had 2 angles. And I'd only have 2 angles here. I would have missed 2 of the solutions. If I want all angles theta between 0 and 2 pi when phi is 2 theta, then I have to take all angles phi between 0 and 4 pi. So if I would in this diagram have to go around twice and find all angles, I'd find 4 pi over 3, 5 pi over 3, 16 pi over 3, and 17 pi over 3. And so you have to figure this out and then divide each of those by 2, and you get the right answer, and you can do that if you want. All right. So I'm saying what I think is the easiest way is to find the two terminal rays and all coterminal angles, then just throw out the ones you don't want. So that's what we did here. We found 4 solutions. And what will happen if this was 3 theta, we would have found 6 solutions. If it was 4 theta, we would have found 8 solutions, right? So you can get quite a lot of solutions if you have trig function of a big multiple of pi, a big multiple of theta equals some number. Maybe I should mention in the book when they do this, Mr. Problem set on the UCO handout, and I think in the book too, they'll state the problem this way: sine of 2x equals this, and they say solve for x, which is perfectly fine. The reason I'm not using that is I want to use x in my unit circle, y in my unit circle. So I'll suggest that instead of doing the problems the way they are in the book, use theta instead of x, and then you won't have a confusion on the unit circle between x up here, the angle, and x over here, the x coordinate in the unit circle. So I have done that for hopefully for clarity. I've used theta for the angle I'm solving for instead of x like the handout does. Okay. Ready to step it up one more. As you can see, each level is really simple, but step, it get pretty high. It's like climbing a tree or something. You ever climb a tree and each step is pretty easy, and then you look down and right, gotta get your parents to come help you down or something. That's what this is. All right, let's try moving it over. Each step is small, but it starts to get quite intensive here pretty soon. That's why we're gonna spend a week on this section. All right, now the next thing is step 4. Suppose I want to solve trig function of a single angle or a multiple angle, a linear equation in a trig function. What's that? That's a name for the following kind of trig of equation. A number a times a trig function plus a number b equals 0. That's a linear equation. Why is it in a trig function? Why am I doing that? Just to give it a name. In algebra, you saw, what do you call this? A equals b equals 0. This is called a linear equation in X, right? This is called a linear polynomial or first degree polynomial equals 0. This is called a linear equation. All I've done, I've replaced X with a trig function, sine of theta or tangent of theta or something. Now it's a linear equation with trig function, still a linear equation in X. These are really, this is a really easy step from the last one, right? If you do the last one, you do this one. What you do is you just put the trig function equal X, and you solve a x plus b equals 0 for x, tells you that by subtracting b, ax equals minus b, and dividing by a, that's just the easiest problem in algebra, right? X equals minus b over a. So what you really want is just replace x with the trig function. You got a times trig function plus b equals 0. Means a times the trig function plus b equals 0. Means the trig function equals minus b over a. That's all you do. Now it's trig function equal a number, you go to step 1, right? So then solve by previous method. It'll be one of your first 3 cases. So if you got a linear equation, trig function, you turn it into trig function equal a number. That's the point. Let's try one of those. It's hard to see this thing right now. Tell me if I turned that too far for you online. Suppose I have this one then. Square root 2. No, that's right. Secant 2 secant theta minus square root 2. That's not right. Go backwards. Square root 2 secant theta minus 2 equals 0. Suppose I give you that equation, right? This is a linear equation and trig function because it's a trig function plus b equals 0, right? Think of this as plus or negative 2. This is a linear equation. If you think of this as a times x plus b equals 0 from algebra, how do you solve it? You subtract b from both sides, getting square root 2 secant theta equals 2. Then you divide by a, right? So you got square root 2 x equals 2. You can put x in here if you want. I think it's not necessary. So I divide by square root 2, and I'll get secant theta equals 2 over square root 2. Right? There it is. Now I've got trig function equal a number. I go back to my previous method, right? Go to method 1. As I said, these things all go back to method 1. So solve for trig function equal a number in a circle. So remember how to solve secant equals a number? Turn it upside down, right? Cosine equals the reciprocal. Square root 2 over 2. I know how to solve that, right? Draw the unit circle. It's method 1, right? Cosine is the x coordinate, so I'll put x equals square root 2 over 2. It's about 0.7 roughly. I observe that the line cuts the unit circle in 2 places, right? This is the vertical line, x equals this number. There's a ray through here and a ray through here. Those are the only possible terminal rays. When I drop the perpendiculars, I notice since this is an x equals square root 2 over 2, this side length is square root 2 over 2. This side length is 1 because it's a unit circle. That forces this other side to be square root 2 over 2. It's a 45, 45, 90 triangle. That must be pi over 4, and this one must be minus pi over 4. I now observe that there are these solutions and any coterminal angles. I'll put 3 dots. 3 dots in mathematics means therefore. Therefore, theta can be either angle plus 2k pi. So minus pi over 4 plus 2k pi, or pi over 4 plus 2k pi. Those are all the solutions to this one. K again isn't. You don't have to write that. Everybody assumes it. Hey, is that one good? Linear equation and a trig function? Well, these are exactly the kind of equations you'll get in your science and engineering and many other classes also. Not so much in business, maybe. You don't do so much trigonometry in business. But chemistry or something like that, you'll do some of this. Certainly electronics engineering, a lot of this. Right. Now, method 5, to solve a quadratic equation in a trig function. These come up fairly often also. They're frequent in our calculus sequence that we have here. What is that? It's a times a trig function squared plus b times the same trig function plus c equals 0. Why would I call that a quadratic equation in a trig function? Because if you let x equal the trig function, you'll get ax squared plus bx plus c equals 0, which is called what? Does that sound familiar? What is that called? Nobody remembers algebra?
Quadratic form.
Yeah, it's called a quadratic equation. And the reason is we call the second degree polynomial a quadratic or a quadratic polynomial. A quadratic equals 0 is called a quadratic equation. So this is a famous thing from algebra, and you know how to solve these. All you have to do is solve a quadratic equation and trig function where you just have a trig function squared plus b trig function plus c equals 0. Is let x equal the trig function to get this. Then solve by algebra, right? What are the ways you know how to solve this by algebra? There's actually 3, but we're only going to do 2 because one of them is superfluous. How would you solve a quadratic equation in algebra? One way was by factoring. Right? Factoring is sometimes difficult, but when it works, it's pretty fast. So factoring is a good deal for a lot of these equations. It's fast. What if it's hard to factor? Then, as already said online, there's a quadratic formula, right? Quadratic formula always works. In fact, what it does is sometimes this has no solution. Like here's a quadratic equation, x squared plus 1 equals 0, right? This is 1 times x squared plus 0 times x plus 1 equals 0. This is positive. This is non-negative. They can't add up to 0, right? So this has no solutions. If it has no solutions, the quadratic formula will tell it to you because it'll give you a square root of a negative number, right? Now, technically, it has imaginary solutions, but we won't do those in this class. So it has no real solutions using a quadratic formula. The third way is completing the square. We won't do that because completing the square is a matter of step-by-step deriving the quadratic formula. So it's the same thing, really, just with the steps written in. No need to do one that does the same thing. But in algebra, you do completing the square because there's some other cases where it comes up that it's better than the quadratic formula for solving other kinds of problems. All right. So this, to get x equals a number, either case, right? Now here's the quadratic formula. If you do this case, you'll get the same solutions, right? These will get the same solutions. The quadratic formula tells you specifically the solutions are minus b plus or minus square root b squared minus 4ac all over 2a. You can have this memorized for the next test. I always have my trig functions memorized. This is so useful. If you take it to calculus, you need it again. And this will really speed you up on the test. Nonetheless, this is an open book test coming up a week. So if you don't want to memorize it, you can look it up. It just takes longer, right? So I recommend that you memorize this again if you've forgotten it. These are the solutions. And remember, if b squared minus 4ac is negative, what's the case? How many solutions do you got? You get square root of a negative, there's no solutions, right? Trying to remind you of the quadratic formula. If b squared minus 4ac comes out equal to 0, what do you get? Square root 0 plus and minus 0 is the same number, you get one solution. This tells you specifically what they are. Square root of a negative, no solution. Square root of 0 plus and minus are the same as one solution. B squared minus 4ac positive, though. One solution for the plus and one solution for the minus, you get two solutions, right? Now you put back x equals the trig function. Right, you substituted x equal the trig function, put back the trig function to get trig function equals these two, 0, 1, or 2.
You might want to move the camera to the side a bit.
Yeah, sorry about that. I was just getting worried. Thank you. All right. So you put back trig function equals this thing now. And this trig function equals a number or two numbers. For each number that the trig function can be, you solve it on the unit circle. So put back the trig function and solve trig function equals number. By step 1 or step 2 or step 3 or step 4, right? And solve. Well, step 4 is not there because that's not a linear equation. Solve the trig function equals a number by one of the first three methods. That's how you solve a quadratic equation in a trig function. Turn it into trig function equals a number and go back to one of your previous methods. Huh? There's more, I think. So let's try one of these off the sheet here. Check the time too. We're getting close to the end. So frustrating to be halfway through a problem, the clock runs out. So here's one off the homework here. When you do it, you can see if you get the same answers. Where did this go? Find it now. There it is. This is 4c. Oh, this is a good choice. Secant squared at theta, we'll write say x. Plus secant theta equals 0. This is an a secant theta squared plus b secant theta plus c 0 equals 0. It's a quadratic equation in a trig function, right? So first thing we do is we let x equal secant theta to get a quadratic equation. X squared plus x equals 0. Now we can solve that by algebra. We can solve it by factoring or the quadratic formula. Which should I use? Quadratic formula is really cool. It works every time, right? But this one factors so easily. Look at this. You pull out the greatest common factor and write this equivalently. It's x times x plus 1 equals 0. I remember pulling out the greatest common factor. See, x to the first is the highest factor they both have. So x times x is x squared, x times 1 is x. Now we have the zero product property, right? What does that say? If the product of two numbers is 0, then at least one of them is equal to zero, right? One or both of them is zero. So this is what's a factor? Factors are things that are multiplied together, right? I factored this, wrote it as this times this. So these are the two factors, the things that are multiplied together. The zero product property says that either this is zero or this is zero, so then the product's zero. So I get equivalently either x equals zero or x plus 1 equals zero. One of those is true, or both. Both can't be zero, they're getting different solutions. So one of these is true. That is x equals 0 or x equals -1. Those are all the possibilities. So you put x equal the trig function, solve it for x, and now our original problem reduces to this. We put back the trig function, secant theta equals 0 or secant theta equals -1 are the only possibilities. This pair of equations is equivalent to the original equation. We just factored to find that out.
Shift the camera, please.
Oh, I thought I had that on the end. Okay. I thought I captured it there. There we go. Something that looks like it. That picture's small. Now, this is a tricky one here. Secant theta equals 0. What angle makes secant equal to 0? I'd like to say, well, cosine equals 1 over 0. Wait a minute, that's undefined. This actually has no solution. If you think about it, secant looks like this, right? It's U shape up, U shape down, U shape up, U shape down, like that. This is y equals secant theta. Right? This is y, and here's theta. When is secant theta equal to 0? Right? It's not. There's no place where this is along the line y equals 0. This has no solution. We'll write this for the empty set. That's the solution to this one. There's no solutions. Secant theta equals -1. How do we solve that? Back to step 1, right? Rewrite it as cosine theta equals the reciprocal, which is also -1, right? So 1 over -1 is also. Now I throw this one out because it doesn't contribute anything. I just have cosine theta equals -1. How do I solve that? Unit circle. This time, remember cosine theta is the x coordinate. This time my vertical line is just tangent to the circle, right? X equals -1 is 1 unit from the origin, so it just touches at one point. Since it touches at just one point, there's only one angle that goes there. It's this one, pi. There's one terminal ray since the circle's only intersected at one point. And it has to be this angle right here, pi. So theta equals pi is one angle to the terminal ray. I guess I better go to the other side. Get rid of this maybe. We'll say one angle to this terminal ray is theta equals pi. All solutions are, this problem may have said 0 to 2 pi. Yeah, it said solve it at 0 to 2 pi. So all solutions are theta equals pi plus 2k pi, but there's only one solution in 0 to 2 pi. Or all, if I ask for all solutions, theta, not restricting it, then you. They're solving that quadratic equation in secant theta. You just factor it, solve for x, and now you've got trig function equal a number, which is the old method. We've got time for one more. This over a bit. These are a little longer problems. We'll do some more of these next time, and we've been doing all special angles this time. Next time we'll have to do some non-special angles. We haven't gotten to those yet either. Let's try this one. This will be 4b. Solve sine squared theta plus sine theta minus 2 equals 0 for theta between 0 and 2 pi. We'll write this notation. Suppose I want to solve that one. Now I put x equals sine theta to rewrite as a quadratic equation, x squared plus x minus 2 equals 0. This one factors, but it's harder to guess the factors, right? You can use the quadratic formula also. But if I'm going to factor this, I need blank times x plus blank times x plus blank to factor, right? What goes on these blanks? Their product is a leading coefficient, right? When I FOIL this times this gives the x squared term, this times x plus this times this gives the x term, and this times this gives this number. So the product of these is equal to 1. The product of these is minus 2. So I'm going to put 1s here, so the product is 1. I could put minus 1s here, but then I factor out a minus 1 and cancel out, so there's no point. And then these two numbers have to multiply to minus 2 and add the 1, it turns out. So I can put 2 and minus 1, and that's how it factors. You can try minus 2 and plus 1, but when you FOIL, you get a minus here. All right, so we'll do a little more factoring next time. But this factors then simplifying. This is x plus 2, x minus 1 equals 0, right? Zero product property to the rescue, right? Either this is 0 or this is 0, one or the other. So either x equals negative 2 to make the first factor 0, or x equals 1 to make the last factor 0. Move the camera over one last time here. Hopefully one last time. I think that's got it. Now you put back the trig function, right? This means equivalently, since x is sine theta equals negative 2, or sine theta equals 1. Two possibilities. What are the solutions to this one? That's right, none of them, right? Sine theta looks like this. It oscillates up and down between plus and minus 1. It's never equal to anything bigger than 1 or less than minus 1. It's never equal to negative 2 down here, right? Never reaches y equals minus 2. So this one has no solution. This is the empty set symbol. Or sine theta equals 1. This one I can solve in the unit circle, right? It's trig function equal a number. Sine is the y coordinate, so I draw the line. Y equals 1. I observe it intersects at only one point. It's tangent to the circle. So I've got only one terminal ray right there. Evidently pi over 2, right? What I have now is theta equals pi over 2 only. If I want all angles, I could put plus 2k pi, right? That's all angles with this terminal ray. But this is the only one between 0 and 2 pi. There it is. How about that? We did a lot of different trig equations. Each step is very simple, but by the time you're done, it's the house of Jackville. It's pretty complicated. So try these problems out in this section. I really want you to try all of these. These are very important problems. So try 7.3. We can't quite do the last one yet because they involve non-special angles. I think we can do 1 through 7. 7.5. Couple more examples like this next time, and we'll do some non-special angles that are in the heart. Everybody have a nice day. Thank you for coming online and to the class. See you next time.
Thank you. Have a good day.
Yeah, thank you.